So our final bit of atmospheric optics to look at is probably the one you're all most familiar with, rainbows. So the reason we hold rainbows for last is because multiple different stages are happening to create rainbows. So you have sunlight passing through water droplets. So again, when you're talking about rainbows, you always have to have the sun at your back and rain in front of you. And then what's happening is you have refraction, and again, different wavelengths, so different colors of light refract at different angles. They change angles as they pass through the water differently. You can see that here. The red changes less, the violet changes more, and then it reflects, and again, this requires that critical angle of water, 48 degrees, bounces off, and then refracts again as it leaves the water. So it comes out, and the wavelengths are still split. So you can see here, violet on top, red on bottom. That's not what you normally think of when you think of a rainbow. That's because for every rainbow you see, it takes multiple raindrops, each one providing its own wavelength. So the upper raindrops are providing red to you, while lower raindrops are providing violet and the colors in between. If you think about double rainbows, similar thing is happening, but it's reflecting twice. So that's why it's not quite as bright. It's because each reflection costs energy. So again, it's bouncing. And again, this, because of the angle of these, that's why you see the inversion back to the normal, where you have violet on top and red on bottom. If you've ever looked closely at a double rainbow, it basically becomes a mirror image of a rainbow stacked on top of it. And that's because literally within the raindrops, there's a second reflection happening.